everybody.
Okay, hi everybody. So today we're still going to do 4.7. I'm just going to do a couple of examples. They're more of word problems so that you can have an easier time on your homework. So let's go ahead and get started. Let's take a look at this example. So it says a car is traveling at 50 miles per hour. When the brakes are fully applied, proceeding a constant deceleration of 22 feet per second. What is the distance traveled when the car comes to a stop? So what they want to know is, what is the distance traveled when the car comes to a stop? So this is what they want to know. And so in the last video, we talked about how if we take the derivative of a position function, we get velocity, and when we take the derivative of velocity, we get acceleration. But when we take the antiderivatives, we can now work backwards. If we have acceleration, we can get velocity using our antiderivatives, and if we have velocity, we can grab our position function if we take the antiderivative of velocity. So let's kind of break down what they gave us and what we know. So right here where it says a car is traveling at 50 miles per hour. So that to me says that that's the initial velocity. So that's when it first started going. So that's the initial velocity. It's traveling at a constant speed right there at 50 miles per hour. So that's what we're going to call our initial velocity. Okay. And then the brakes are fully applied, so that means that it's going to start decelerating at 22 feet per second squared. Okay, so here where it's a deceleration, what comes to mind for me is the acceleration function. So this tells me that this is going to be a of some function t, and we are going to set this equal to -22. And the reason we're going to set this equal to -22 is because there's a deceleration. We're not accelerating. We are actually getting slower because we applied the brakes. And they want to know what is the distance traveled before the car comes to a stop. So they want to know that. Okay, so let's write down what we know down here. So let's work out our solution over here. So we know that A of t is equal to -22. So we know A of t is equal to -22, but we want to know the distance traveled. So if we want to know the distance traveled, that means that we're eventually going to need to look for that position function. And we only right now have acceleration. So that means we're going to have to take the antiderivative of acceleration in order to get that position function. Eventually. But when we take the antiderivative of acceleration, we're of course going to get velocity first. Okay, but that's not all we know. So let's see what else is given. So this was given to us, the A of t is equal to -22. What else was given to us? Looks like they also gave us the initial velocity. So remember that initial conditions can help us find the constants during after we take the antiderivative. So what we're going to do now is let's write this down formally. So what I'm going to do here is I'm going to write that the initial velocity formally. So what that means is that v of 0, since it's the initial velocity, it's at the time when time is 0, the velocity was 50 miles per hour. But now I want you to be really careful here. The problem here is that they gave us miles per hour, but here we have feet per second. So what we need to do is we need to do a conversion. So there's two ways you could go about this conversion. You can say, okay, well, 50 miles per hour, and then turn it into feet per second using the conversion in fraction form. So that would be 5,280 over 3,600. And for this, you could really just look this up what the conversion is. And when you multiply that out, you'll get 220 over 3 feet per second squared. Okay. And now after that, we are going to, another way you could have done it is if you would have looked it up on the internet, you could have also gotten the decimal value. So you could have done 50 times 1.466 to go from miles per hour to feet per second times 1.6667, and that's going to give us a 73.335 feet per second. Okay, so this is something that now we know, and this gives us our initial velocity. And remember that this at the end of the day is going to help us. I'm going to use this one for this problem just because I like to keep things exact, but this is going to help us find that constant after we take the antiderivative of a of t. So let's go ahead and take that antiderivative of a of t. And remember, when we take the antiderivative, we're going to actually get the velocity function. So we're going to get v of t. So we take the antiderivative. So this is just a constant. It's all by itself. So what the antiderivative of this is going to be negative 22t plus c. So remember that you always can check this by saying, if I take the derivative of my velocity, am I going to get negative 22? And the answer is yes. But remember, it varies by a constant. But now we're going to use our initial condition here, our initial velocity, and say since v of 0 is equal to 220 over 3 feet per second, then if we plug that into our velocity function with the unknown constant, then we're going to get 220 over 3 is equal to negative 22 times 0 plus c. So this tells us that c is just equal to 220 over 3. So c equals 220 over 3. And that usually tends to happen with these problems. I'm not going to say it always happens because it doesn't, but for the most part it does. So that's what c is equal to. And now what we're going to do after that is, now we know what that constant is equal to, so we know what our velocity function is equal to. Our velocity function is equal to negative 22t plus that 220 over 3. Okay. And now we're one step closer to finding the distance traveled, because all we need for the distance traveled is we need to find that position function. Okay. But before we actually find the position function, we could actually do it now. But what I want to do before we go ahead and do that is that what I want to take a look at is, how are we going to know when the car comes to a stop? We want to know the distance traveled when the car comes to a stop, but we need to know at what time that car comes to a stop. And so the car will come to a stop when the velocity is no longer changing. And so that happens when v of t is equal to 0. So to find when the car comes to a stop, that's going to be v of t is equal to 0. So let's write that down. So note, the car comes to a stop when v of t is equal to 0. So we don't know when that's going to happen, but we can easily find that out. So what we need to do now is set v of t equal to 0 to find out when that time is going to make the velocity stop, and then we can plug that time into our position function once we find it. Of course, you could have found your position function first and then gone back and done this step, but we're already here, so let's just do it. So we get 0 is equal to negative 22t plus 220 over 3. And so now what we need to do is solve for t. So let's solve for t. So if we solve for t, we're going to end up with, we're going to move the 220 over to the other side. Sorry, you can't see my movement. 220 over to the other side and divide by negative 22. And that's going to give us a time of 10 over 3. Okay. And so like I said, I'd rather keep this exact just for the sake to avoid error in our problem. Okay, so this is what we're going to use to find our position function. So now let's find out our position function. So then we need to find S of t. Okay, now let's go back for 1 second. I actually want to go back. So to find S of t, remember we have to take the antiderivative of v of t. Okay, so to take the antiderivative of v of t is we're going to use this. So we need to take the antiderivative of negative 22t and this, and then we're going to add that constant because remember antiderivatives can vary by a constant. Okay, so if I take the antiderivative of negative 22t, I'll do it here quickly and then I'll rewrite it in the other page, is remember that we're going to add 1 to this exponent. So there's an exponent of 1 here plus another 1. And then we're going to divide by that 1 plus 1. And so when we do that, we're going to get, of course, we're going to get t squared. But then there was a negative 22 in front of it. And then we have to divide by 2. So then we're going to get negative 11 t squared. So this antiderivative is negative 11 t squared. And then for the other piece, it was just a constant. So now to get the antiderivative of that, that's going to be 220 times t. Plus 220 over 3 times t, plus that constant that it can vary by. Okay. But now we know that we're eventually going to need to plug in the fact that t is equal to 10 over 3 into our function. But the thing is, if we do that now, that's not really going to help because look at this. Then we're going to vary by c. So we actually need to find this c before we plug that in. So how do we find this c? We need an initial condition for the position, right? But we don't really know the position. We just know the car is traveling at 50 miles per hour. So if we consider when s of 0 is equal to 0, so before time started, the position didn't move and it didn't matter. So when s of 0 is equal, so when time is 0, s is equal to 0 because it hasn't moved from its starting place of that car traveling. So the car hasn't traveled. So you have a little car here, right? And it's traveling 50 miles per hour. If time is equal to 0, the position hasn't changed, so your position is actually going to be equal to 0. Okay, so now that we know that, we can plug that information into our function here in order to find that function, in order to find c. So since s of 0 is equal to 0, if I plug in 0 into this function, I'm actually not going to write this down because you might actually see where this is going. If time is equal to 0, here's 0, 0, 0, everything gets zeroed out, and so c is forced to equal 0. So if I plug in s of 0 is equal to 0, we'll actually find out that c is equal to 0. And so that tells us that our position function looks like this. So sometimes they don't give you all the pieces, and it's up to us to kind of think about what's happening to the function in order to find out these initial conditions, because sometimes it's not telling you it's not moving. But if we actually think about what's going on with the problem, if time is equal to 0 and I haven't started moving yet, then my position's not going to move. So that distance is going to be 0. I haven't traveled anything. Okay, so now that we have that, we're going to plug in our t equals 10 over 3. And that's because we wanted to know how far we traveled when the car came to a stop. And the car came to a stop when v of t was equal to 0. So when the velocity was no longer changing. Okay, so after that, we're just going to plug that into our function here. So we're going to get s of 10 over 3 is equal to 11 over 10 over 3 squared plus 220 over 3 times 10 over 3. Beautiful. Okay, now after that, we just simplify. And if you plug this into your calculator, you'll get that we went 122.2 feet in distance. And so here we don't have to put per second because they want to know the distance traveled, right? So that's all they want to know. So let's do one more example, and I think you should have everything to be able to finish your homework. You should have really been able to do your homework without this information, but I just wanted to go ahead and give you a little push so that you guys, if you guys didn't understand the word problems too much. Okay, so let's go ahead and do another example. Okay, so let's consider an object falling. The acceleration downward is g. So what they mean here, if you've taken physics courses, our acceleration when we throw something down, for example, like if I drop my pen down, it's just gravity. Nothing else is pulling it down other than gravity, right? We don't have any external force going like this, so gravity's pushing it down. And so we're going to call that a downward g. And this is equal to, so this is actually, I'm not sure if they put this in your textbook or not, but you should know this for your records, is that gravity is approximately 9.8 millimeters per second. 9.8 meters per second squared. And if you convert that into feet, it's 32 feet per second squared. So just use whichever one you need for the problem. For your homework, you might need to use one or the other depending on the context of the problem. But let's continue reading. So this here is important for you to know for your homework. So they might not give you the accelerate, like if they on the homework they ask you about a ball getting thrown, you need to know that the acceleration is going to be your gravity. And if it's getting thrown downwards, it's going to be negative. So for this, I'm just telling you what gravity is equal to, and then we'll apply the negative when we write the formula for acceleration. Okay, so if a bouncy ball is dropped from the top of an Empire State Building, and they're telling you that the Empire State Building has a height of 443 meters, find when it hits the ground. So they want to know when it hits the ground. So what they want to know is when it hits the ground. Okay, so let's say we have this building here. You're throwing something from here, and you want to know when it lands down here. Well, let's pretend that's leveled. Right, so they want to know when it has that position right there. So what they really want to know is when is that position equal to 0? When is the height equal to 0? And so for that, we need to find out when s of t, our position function, actually equals 0. And we don't know when that happens. And so this problem is actually different than the last problem, because in the last problem, they wanted to know the distance traveled. Here, they want to know when it hits the ground. They're telling us that s of t is going to equal 0, but they want to know at what time. So our job here is to find that time. So let's see what we know. So we know that our acceleration is due to our gravity here. So we know that A of t, always a good habit to write down everything you know about the problem, especially for these problems. We know that A of t is equal to 9.8 meters per second squared. And so the reason I'm actually using the 9.8 is because in the problem, they gave me the height in meters, so might as well just keep that in meters. So I gave you this so that you have help in your homework depending on the problem that is given to you, because you might use one versus the other. Okay, so now our job is, let's figure out what else is going on with the problem. So also, maybe we'll do this part. No, we do. We know the initial conditions for this, actually. So when they told us that the building is 443 meters high, they're telling us that this part here is 443 meters. So when we're first here at the ball, our initial condition for the position is this height right here. So that tells us that S of 0, before we even throw the ball, is actually 443. So we have one initial condition. Another initial condition that's not in the context of this problem right now is that V of 0 is also equal to 0. Because at the time that before you even throw the ball, you haven't thrown it, you haven't done anything, you're still just right here, this little ball. You're not using any velocity at that moment. So at first, your velocity is just equal to 0. So these are our two initial conditions that we know, initial conditions. Okay. And if you're in your physics class, you'll see this a lot in your physics courses. Okay, so now let's go ahead. We know we're going to take the journey to find S of t, so let's go ahead and just find V of t. So V of t, right, so the antiderivative of this is going to be negative 9.8. I'm going to leave the meters meters per second off, t plus c, because it's just the antiderivative. Negative 9.8 is just a constant, so this is our derivative. So remember that V of 0 is equal to 0. So if I plug in V of 0, which equals 0, I'm going to get that c is still equal to 0. So our velocity function, so V of t is equal to negative 9.8 t. So that's our velocity function here. Okay. And now what we need to do after this is we need to find our position function. Okay. So to find our position function here, we need to take the antiderivative of our velocity function. So let's do S of t. So we get 9.8 t squared over 2. Then after that, we need to do that plus c. And so if we simplify this, this actually is going to equal this is going to equal negative 4.9 t squared plus c. And remember that we know the initial condition for our position. Our position was initially at the height of 443 meters, so we can plug that in. So since S of 0 is equal to 443. If we plug that into our function, we're going to get S of 0. We're going to get 443 is equal to negative 4.90 squared plus c. So this tells us that c is equal to 443. So our position function is S of t is equal to negative 4.9 t squared plus 443. Okay. So sometimes it actually is a good idea to go back to the problem and see if this really makes sense for this problem. And I bet you anything it will. Because if I look at this picture, right, it's not a very good and drawn picture, but maybe if I do something more like this and I draw it a little bit better, right? If we just drop the ball like this, it looks like half a parabola, right? And it's going downward. And my height here is 443. Well, that's all that your position function is it's a parabola going downward, shifted up at 443, but then we're considering how it's changing right here due to gravity. So that's what our S of t is. So now we want to know when it hits the ground. So in order to find out when it hits the ground, That tells us that if it hit the ground, then the position is no longer at 443. The position is now at 0. So here, the most that the position is 443, and then it's going to go drop down to 0. So they want to know when it happens down here. So that's what we're going to go ahead and do, is we're going to find out when S of t is equal to 0. That's what we want to know. And so remember that S of t was equal to negative 4.9 t squared plus 443. And we want to know when that equals 0, because that means it hits the ground. So what we're going to do now is solve for t. We're going to move that 443 over to the other side and divide by 4.9 to get that t squared is equal to 443 divided by 4.9. And then we're going to take the square root of both sides. Okay, well, when we take the square root of both sides, I know that we initially write plus or minus, but it doesn't really make sense to make negative time, right? We're not talking about past, we're talking about present, moving forward. So what we're going to do is just leave it like this, because we know that our time has to be positive. And so from there, we just take the square root, plug this into our calculator, and so that tells us that t is equal to the square root. If we simplify 443 over 4.9 is the square root of 90.408, which is approximately 9.508 seconds. Okay, so that's the end of the problem. And you could always check the answer by getting 9.8, getting our time here, and plugging it back into this function here to make sure that when you plug it in, you do get a position of 0, so that you know it worked out. Okay, so that's it. That's it for 4.7. Most of the word problems are a lot like this, where you kind of have to dig for some information. They give you some of it you kind of have to think outside the box and go, wait, what's really happening at my initial conditions? These initial conditions are super important. And again, please let me know how you're doing on the homework.
Help! Tell Nina you need help. She can't help you.
It's super crazy right now. So if you don't tell me that you need help with the homework, if you don't tell me that you have a lot going on, then I won't know. So I need to know so I can best help you as much as I can, right? We still have to do the homework. We still have to learn the material, because a lot of us are moving on to Calc 2, but I really want to know how you're doing and what I can do to help you in this course. So please keep me updated on everything, especially if you're having issues with whatever, internet issues, you have to babysit your brother or sister, that's fine, but communicate with me. That's what I need. Because if you don't tell me, then how am I going to know? So always, 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 please let me know. I will always try my best to help you. But you got to meet me halfway. Okay? So see you in the next video.